All right, so let's continue where we left off. We are moving through the first practice exam for Stat 520. We completed number one. Now we're looking at number two. Finished part A, not separable, therefore not independent. Part B, we identified the CDF by a double integral, and then we use it to calculate a probability. Now in part C, we want to find an expectation of 7x1 squared x2 cubed. All right. And then what we want to do with that is we want to go ahead and also express it as a conditional expectation. Okay, so let's see what we got. Part C, we're looking at the expected value of 7x1 squared, x2 cubed. So straight up, just finding that expected value would be as a double integral, integrate the quantity times the PDF, and I'm using X1s and X2s because we are working with the actual expectation, not a CDF or anything like that. That's how we set up our integral, then just a matter of distributing and integrating. 0 to 1, 0 to 1, 7x1 cubed, x2 cubed, plus 7x1 squared, x2 to the fourth power, dx1, dx2. As we said last time, if we're doing dx1, x2 is treated as a constant, and vice versa. And so we end up with 7/16 plus 7/15 as our answer here. Or if you need to simplify it a little bit more, 7 times 31 over 16 times 15. If you need to simplify more than that, use your calculator. All right, so that's part C. The first part of part C, I should say. The next part is we want to specifically use, let me expand this here. We want to specifically use conditional expectation to set up, but not evaluate an expression for the expected value in this context, right? Using conditional expectation. And so let's go ahead and see if we can apply that. Now, note that we want to find an unconditional expectation using conditional expectation. So recall that the expected value of y given x, when we apply an expected value to that, right? So this expected value in purple is expected value in which y is treated as random, x is constant. The green expected value is where x is treated as random, as it genuinely is. This is an iterated expectation and yields e of y. Okay, so that's the principle we're going to use. Thus, we can say expected value working in reverse with this formula of 7x1 squared, x2 cubed is the expected value of 7x1 squared, x2 cubed given, and we can choose x1 or x2. I'll just choose x1. Okay, and so that is an expression that we can use to represent this iterated expectation. Okay. So, this outer expectation will be the integral from 0 to 1, integrating against the x2 density. Okay, I'm sorry, the x1 density of dx1. Whereas the inner expectation would be the integral of 7x1 squared, x2 cubed times the joint over the x1 marginal. Okay, that's a conditional density that we're working with right there. Okay, of course we'd have the x1 density out there. Okay, and we're integrating from 0 to 1 in here since they're independent. And you can see explicitly how this expression is essentially the same expression we calculated earlier. So I'll just leave it at this. Suffice it to say, if we proceed, we'll get the same answer. This one just kind of requires us to identify the density. So we can show that f of x1 is equal to integral 0 to 1 of x1 plus x2 dx2, which would be x1 plus 1/2. Plug and play. Have a great day. Alrighty, so that's number 2. Number 3 is a bivariate transformation. We have a joint density. We're given these values. I'll just work through this one real quick. Generally speaking, I think this is one of those areas of confidence for most students. And so I'll work through it real quick. So recall that the formula is that f in terms of y's it's going to be our h evaluated at w inverse of y1, y2, w2 inverse y1, y2 times the Jacobian on the inverse functions living in the support. Okay. All right, so let's go ahead and find the inverse functions. Okay, so we can easily see what x1 would be. It's y1 over 2. Okay, whether you're doing a univariate or a bivariate transformation, you're always solving for the new variable as a function of the old variable. Okay, so x2 would be y2 plus y1 over 2. Okay, let's scratch that. Okay, so anytime you're doing a bivariate transformation or a univariate transformation, you're always solving for the old variable in terms of the new. So we can see x1 is y1 over 2. That's your inverse, right? And as a result, x2 is going to be y2 plus y1 over 2. Right, y2 plus x1 when we bring that over to the other side. Okay, so we got an inverse transformation. We're going to plug it into the original function, and we're also going to find the Jacobian. Okay, so our Jacobian is going to be dx1 dy1, dx1 dy2, dx2 dy1, and dx2 dy2. Okay, so x1 y1 is 1/2, x1 y2 is 0, x2 y1 is 1/2, x2 y2 is 1, Jacobian is 1/2. All right, let's bring everything together in the formula. Let's call this formula star. Okay, we're going to get 2e to the negative x1 minus x2. Switching the order right there. Multiply that by the Jacobian. And we'll rewrite the support accordingly. 0 less than x1 less than x2 less than infinity. Okay, so our 2's cancel. And we end up with e Twos cancel, we end up with E. So our twos cancel, we end up with E. So our twos cancel, and we end up with E to the minus Y1 minus Y2, which is start feeling familiar. So, solving the support, those cancel out. And so one of the bounds ends up being 0 less than Y2 less than infinity. Okay. And then on the flip side, we can also say that this inequality can be extended on the left by saying negative infinity less than 0 less than y1 over 2 less than y2 plus y1 over 2 less than infinity. So just to make it more explicit, when we subtract that y1 over 2, okay, of course the infinities won't be moved by it, but this ends up giving us 0 negative y1 over 2 negative infinity, which will lead directly to this other part of the inequality. Okay, so what this is the product of two independent exponential one random variables, whereas we started with two dependent random variables initially. Alrighty, from a triangular to a rectangular support. And that solves the problem.